Hello, statisticians. Today's lesson is on the multiplication rule. Let's get started. In 1962, the NBA player Wilt Chamberlain scored a record that may never be broken, scoring 100 points in a single game. For reference, in the NBA, scoring 30 points in a game is considered a very good performance, so 100 is truly unheard of. And in the history of the game, only one other performance has even come remotely close, and that was Kobe Bryant's 81-point game in 2006, which is the second most ever scored by a player in a single game. Now, when a performance like this happens in basketball, it's often said that these players have a hot hand, meaning that they are especially good or especially on their game that day. Their hands are so hot, it's as if they can't miss any of their shots. However, some statisticians and data scientists argue that there is no such thing as a hot hand. Instead, they say that high-skill players also sometimes just get especially lucky. They argue that if you play enough games and take enough shots, you're bound to have an especially lucky shooting day at some point. So, is the hot hand real, or do some players just get lucky on some days? That's going to drive our question for the day. Do players get hot hands? With that question in mind, let's turn to our notes. To explore the hot hand, we first need to look at some additional properties of probability. And we're going to start with the multiplication rule. This is the multiplication rule, the probability of A and B. Recall that the upside down U looking symbol means and. It is equal to the probability of A times the probability of B given A. Now, we'll explore this formula in more detail later on, but first, we're going to show you how to approach these sorts of problems using the method we've recommended for most probability problems. Before going straight to the formulas, we're going to try to use our reasoning and the keys to probability. For these keys, today we're solving multiplication rules, and we're going to focus on utilizing these two, drawing the problem first, and then multiplying the ands. To show you more about what we mean, let's discuss a type of drawing that we will find very helpful in probability problems, tree diagrams. Imagine that a student is wondering about their chances of getting admitted into their dream college. With some extracurriculars and teacher letters, the student has a good chance of getting in, so long as their academic qualifications are up to par. Their goal: finish high school with a GPA and ACT score that puts their academic qualifications in the top 50% of applicants to the college. So, for this scenario, we're going to categorize this student's academic performance like this. Higher rank means their GPA and ACT are in the top 50% of applicants to the college, and low rank means they're in the lower 50%. So, imagine that the student has a 65% probability of finishing high school with a higher rank. If they are in a higher rank, then they have an 83% chance of being admitted. If they have a low rank, then they have a 39% chance of being admitted. What is the student's probability of finishing with a higher rank and getting admitted? So, to help us wrap our heads around this question, we're going to first draw it out. And when you have a scenario like this, where there's a lot of, if this is true, then this is the probability. And if that is true, then that is the probability. In other words, a lot of probabilities are dependent on other outcomes. It's helpful to draw a tree diagram. So let's focus on the first part of the setup. The student has a 65% probability of finishing high school with a higher rank. So I can make a tree branch that looks like this, with the probability of a higher rank labeled as 0.65. Now, if I want to find the probability that they don't finish high school with a high rank, I simply do 1 minus 0.65, and the remaining probability of 0.35 is the chance that they finish with a lower rank, and we can draw that as the other branch outcome like this. So, the problem then states that if they finish with a higher rank, then we continue to work on the upper branch. And they now have an 83% chance of being admitted into their dream college. So again, we draw another branch like this. And we'll do 1 minus 0.83 find the probability that they're not admitted into their dream college. So there's a 17% chance that if they had that higher rank, they would not be admitted into their dream college. Now, we're going to move on to that lower branch. So they've had a lower rank in high school, and the question states that even in that case, they still have a 39% chance of being admitted to the college. 1 minus 0.39 equals 0.61. So at that lower rank, they have a 61% chance of not being admitted. And now we have our full completed tree diagram. So let's return to the question we were asked. What is the student's probability of finishing with a higher rank and getting admitted? So for the notation, let's use H to represent the event of finishing high school at the higher academic rank, and let A represent the event of being admitted to the college. So this question is asking for the probability of the higher rank and the probability of being admitted. This means that we follow the upper path of finishing at the higher rank and following the upper path again of being admitted to the college. So now we want to find the value using our third key to probability. Multiply the ands. So to find the probability of finishing at the higher rank and getting admitted, we multiply the probabilities along that path. And that gives us a value of 0.54. So the student has a 54% chance of finishing at a higher rank and getting admitted. Now, let's return to the multiplication rule formula and see how we could also use this in the same scenario. By the multiplication rule, the probability of H and A is equal to the probability of H times the probability of A given H. Probability of H is the probability of finishing at the higher rank, which is 0.65, times the probability of A given H, which is described by the last branch, showing the probability of getting admitted given that they already had the higher rank. So times 0.083, multiplying those together, gives us 0.54, which is the same answer we found before. So using the formula or the keys to probability, we end up in the same place. Now, imagine we were asked to find the probability of a student getting admitted in general. Well, there are two ways they can get admitted. We've already calculated the probability that they get admitted with a higher rank. They also could have gotten admitted by finishing at a lower rank. So we need to calculate that next. So they could get a lower rank and also be admitted, and means multiply. So there's a 14% chance that they would be admitted at the lower rank. And since there's two ways that they could be admitted, through the higher rank or the lower rank, we're going to add those together, and there's a total of a 68% probability of being admitted in either way. Finally, let's look at the probability that a student had a higher rank given that they were admitted to the school. As we saw earlier, we are going to go back and review that other key to probability where we divide by the givens. So we're looking at these two paths where we are admitted. We don't care about the rest of the tree diagram, just this one condition. So the chance that they are admitted is 68%, and using that key to probability of dividing by the givens, that gives us our denominator of our fraction. And out of those 68% of times where the student is admitted, we want to know which of those times do they have the higher rank, and that is the first branch, which is the 54% of the time. Dividing those out gives us 79%. So there's a 79% chance that a student has a higher rank given that they are admitted. Now, let's return to our final topic, repeated events. So imagine we are flipping a fair coin. What is the probability of getting a heads 5 times in a row? Well, we can describe the first flip of a coin with branches like this, 50% heads, 50% tails. And then we can flip the coin again to get an additional set of branches. And then we can flip the coin a third time. Now, note for simplicity that I'm going to only now draw the branches on the top branch, showing the path that we're interested in getting heads each time. And then we flip for a 4th time and a 5th time. So we're interested in only the top path getting a heads 5 times in a row. which can be expressed as a probability where we get a heads, and then a heads, and then a heads, and then a heads, and then a heads, 5 times in a row. And we know from rules of probability that we multiply the ands. So to find the probability, we multiply the 0.5 5 times in a row, which could be expressed as 0.5 to the 5th power. And that comes out to 0.03, or a 3% chance of getting 5 heads in a row. Now, as you can see from that example, drawing a tree diagram can get tedious when we're describing events that are repeated many times. So in these cases, with repeated events, multiplication without drawing the tree diagram is possible. Let's look at another example. Returning to the context of basketball, a free throw is a penalty shot in basketball. One of the NBA's best free throw shooters is Stephen Curry. He makes 90.6 of the free throws he attempts. Assuming his probability of making free throws is the same at every attempt, what is the probability that he makes 6 free throws in a row? So the probability of making 6 in a row is the same thing as the probability of making the first, and making the second, and making the third, etc. Which is the probability of making the first one is 0.906 times 0.906, 0.906, etc., 6 times in a row. So we can write this as 0.906 to the 6th power. And when we calculate that, we find that Curry's probability of making 6 shots in a row is 55.3%. Now, let's look at another example. Let's say Curry is fouled in making a 3-point situation. So he will take 3 free throws at a time. And we are asked, what is the probability that he makes the first 2 but misses the last one? So we're going to find the probability that he makes the first one, makes the second one, and misses the third one. We already know that he makes the shot 0.906% of the time, and then to find the probability of missing one, we do 1 minus 0.906 to get 0.094. And this probability would work out to 0.077, or 7.7%. Let's look at one last example. What is the probability that he makes at least one of his next 4 free throws? Well, making at least one means making 1 or more. And the only outcome that doesn't fit that definition is making 0 or none of them. So that means it's the complement of that. So we're going to find the complement of making no shots. So we're going to find the probability that he makes none of the shots, which is 0.094. He does not make the first one, does not make the second one, does not make the third one, does not make the fourth one, and then find the complement of that value. So 0.094 to the 4th power, and then find the complement of that. And that gives us 0.99992. So Curry has a very high probability of 99.992% chance of making at least one of his next 4 shots. And in general, when you are in an at least one scenario, you can approach it by using the 1 minus complement of none. So now, let us go back to what we started with in our initial question. The hot hand theory, or the theory that on some days, players are especially on their game. In other words, are they better than usual? So some statisticians argue that the hot hand is not real. Instead, they argue that high skill players just have lucky days. The underlying probability of making shots is still the same, but they happen to have more free throws in a row, or more shots made in a row, just by chance. It's similar to flipping a coin and getting a bunch of heads in a row. It can happen. So if anyone would have had a hot hand, it would have been Kobe Bryant during his 81-point game. So let's explore that data in more detail. Specifically, let's analyze the 3rd quarter of that game, which may be the best quarter of basketball ever played by a single player. For context, Kobe's team, the LA Lakers, were playing the Toronto Raptors. At the beginning of the third quarter, the Lakers were down 49-63. So Kobe stepped onto the floor. At that point in the game, he had already scored 26 points. He missed the first shot of the quarter, which was a three-pointer from the floor. Then he missed the second shot, but from here, he went on an absolute tear. He made a layup, which brought his total points up to 28. Then he made a jump shot, moving his total up to 30. Then he made another jump shot. Then he made a three-pointer, and another three-pointer, and then another three-pointer. Then he made a jump shot from the baseline where he was fouled. He then made a free throw afterwards, and then he made another three-pointer. And finally, he showed he was human by missing a shot after this incredible streak. Then he made a layup, and he made another layup. Then he made a dunk, and he missed the last shot of the quarter. And by the end of the quarter, his total had jumped up to 53 points. As I had shared at the beginning of the quarter, Kobe's team was down 49-63. But by the end of the quarter, they were up 91-85. And as we know, by the end of the game, Kobe had scored 81 points. The rest of the Lakers team had only scored 41. So, did Kobe have a hot hand that game? Well, over his career, Kobe was a 44.7% accuracy shooter, meaning that he made 44.7% of all the shots he took. In that third quarter performance, he made an incredible 8 consecutive shots from the field. Given this performance, we can ask, was his probability of making shots that day higher than normal? So let's assume that the hot hand does not exist. Let's imagine that Kobe's shots were all of equal probability of going in, no matter the day. So under that assumption, what would be the probability of Kobe making the 8 shots in a row like he did that day? Well, we'll be assuming that the probability of him making a shot is equal to his career percentage of 44.7%. So making 8 in a row would be 0.447 times 0.447 times 0.447, 8 times in a row, or 0.447 to the 8th power, which comes out to 0.00159. This means that it's not very likely that he would have made these 8 shots in a row. It's less than a 1% chance, 0.159%. Pretty unlikely. So that is some evidence in favor of the hot hand theory, right? Well, in order to keep that in mind, you need to think about how many shots he took over the course of his career. He took 30,697 shots. So how many shots would we expect him to have come up with 8 times in a row like that? To determine that, we need to look at a simpler problem. Let's say that he only took 8 shots in his entire career. How many times could he have come up with 8 in a row? So if he only took 8 shots in a row, then it's only possible that he could have gotten one streak of 8 in a row. But if he took 9 shots in his entire career, he could have gotten the first 8 and missed the last one, or he could have missed the first shot and gotten the last 8, and there's 2 chances that he could have gotten an 8 streak finish. And just kind of a side note, if he had made all 9 of them, that would still count as an 8 streak. Now let's say he got 10 shots in his entire career. In order for him to get 8 in a row, he could have made the first 8 and missed the last 2. He could have missed the first one, missed the last one, and made the middle 8. Or he could have missed the first 2 and made the last 8. So you should see a pattern here. And the pattern is that the total number of possible times that you could get 8 in a row across a career is the total number of shots you took minus 7. So how many opportunities did Kobe have to get 8 shots in a row? And that includes from one game to the next game, including wraparounds. So in his career, he took 30,697 shots, minus 7, which means that he had the opportunity to get a streak of 8 shots made in a row 30,690 times. So if we want to figure out how many times would we expect this to happen throughout his career, we take the probability of getting an 8-streak game times the number of chances it happened, and we would expect that just purely by chance in his career, he should have had 48.8 games where he had 8 streaks in a row, 8 shots in a row. And it actually happened 47 times throughout his career. So not too far off the real answer. So that brings us back to our original question for the day. Is this enough information to disprove the hot hand theory? If yes, how so? If not, what other evidence would you like to see? So take a moment to jot down your initial thoughts to these questions, and we'll discuss them further in class. That's it for today's statisticians. We'll see you next time.